Okay, so a practical application with acid-base reactions is to do a titration. Instead of having to do all the math, you can use what's called titration to find the amount of either acid or base to neutralize a reaction. And so this is also called volumetric analysis. It's a technique for determining the amount of a certain substance by doing a titration. So titration involves delivery of a measured volume by burette. A burette is a really tall, thin piece of glassware, of a solution of known concentration, which is called the titrant, into a solution containing the substance being analyzed, which is the analyte. So for example, let's say you had an unknown concentration of acid. You're going to add a known concentration of base, and once it reaches a certain point, which we'll talk about, then based on the amount of base that you added, you could figure out the concentration of the acid, kind of like in the example that we just did. So the equivalence point is when enough titrant has been added to react exactly with the analyte. So this is the point that you're looking for, because you don't want to go past that. You want to react with just enough so that it's neutralized. A way to tell that that has happened is by adding what's called an indicator, which is a substance added at the beginning of the titration, and it changes color at the equivalence point. And so, for example, phenolphthalein changes color between basic and acidic solutions, and so as soon as it changes color, you know that you've neutralized your solution or gone right past that point. So the end point is where the indicator actually changes color. It's where it changes color and sticks, and we'll do a lab with this, but it will start to change color but then go away as some of that solution is changing pH, but not completely yet. And so we'll do a lab and hopefully that will help. So let's take a look at a couple pictures of this. So here's your burette. It's a really tall piece of glass. You've got the stopcock that you can turn to adjust the flow of liquid into the flask. And here you've got either your acid or base and the indicator. This is your unknown concentration. And in the burette, you've got either your base or acid of known concentration. So if you take a look at this picture, this is using phenolphthalein as an indicator. So you've got it in here, but it does not a color at all. So here you're adding a little bit more, and you can see you've got a couple little dots of pink, but it's not staying. Here's where we reach the end point, and it's very pale pink, and it's staying pink, so we know we're very close to the equivalence. And here it's way pink, you went too far. So this experiment involves a lot of care because you got to take your time and be patient. Okay, let's look at another example. So a student carries out an experiment to standardize a sodium hydroxide solution. We're going to neutralize it. So we have 1.3009 grams of what's called KHP. It has one acidic hydrogen, and we're dissolving that in water. So we're making our solution, our known concentration of acid. We're going to change our volume, so we're going to add 41.20 milliliters of NaOH. And we want to find the concentration of NaOH. Okay, so first thing we want to do is write our reaction. So we've got our KHCH4O4 plus NaOH. And if we look at all the species involved, because this has one acidic hydrogen, the potassium is going to come off and then leave this as our acid. And then we know Na and OH will break apart. So really our overall reaction is our HCH4O4 plus our OH minus, and then the acidic hydrogen is going to come off, so we're going to produce our water, and C8H4O4 as our other species. Okay, so now let's put down some information. We've got 1.3009 grams. Our change volume of our OH was 41.20 milliliters, and we're looking for the molarity or the concentration of the NaOH. So if you look at this balanced net ionic equation, everything is 1 to 1. Okay, so to find molarity, we need moles per liter, which means we need the moles of the OH minus. So if we can find the moles of our acid, because everything's 1 to 1, that'll give us the moles of the OH minus. So we know that we added 1.3009 grams of our KHP. So I'm just going to write KHP instead of that entire long thing again. And they were really nice and gave us the molar mass. So for every 204.22 grams, we know that's 1 mole. And so I've already done this calculation for you, and that gives us 0.00637 moles. Now this is moles of KHP, but it's also moles of NaOH because everything is 1 to 1 to 1. And so if this is my moles of KHP and NaOH, and I want to find molarity, which is moles per liter, I'm going to take those moles divided by the volume of NaOH. Well, here it's in milliliters. I'm just going to move my decimal 3 spots. So 0.04120 liters. If I divide that, I get 0.1546 molarity of NaOH. Now let's look at our significant figures. I'm seeing 4 and I'm seeing 5, so it looks like 4 is okay. And that's our molarity of NaOH. Let's look at one more example. Okay, a chemist analyzes an effluent or a waste material that contains CCl4 and HC7H5O2. It's a weak acid that has one acidic hydrogen. Okay, we're mixing the waste material with 0.3518, or we've got 0.3518 grams of that mixed with water. And we have 10.59 milliliters of 0.1546 molarity NaOH required to neutralize it. So we want to calculate the mass percent of the weak acid that's in the original sample. Okay, we need a little bit of room to write this, so we're going to go to the next page. So first thing we want to do is get all of our species. Well, CCl4 is not going to be included in the reaction. It's not an acid, it's not a base, it's not going to be neutralized, so we're not going to include that. So instead we've got our weak acid, HC7H5O2, plus our NaOH. Well, we know the Na is going to break apart from the OH minus, so it's going to leave us just the hydroxide. We know that hydrogen is going to come off from the weak acid, so we're going to produce water. And then whatever is left, which is our C7H5O2. Okay, now let's write down some of our information. We know of the total waste material, we had 0.3518 grams. And then for the NaOH, we know we added 10.59 milliliters, and that it was 0.1546 molarity. So we want to find the percent mass of the acid in the total waste material. And so in order to do that, our first step is going to need to be moles. Well, again, everything is 1 to 1 to 1. So we need to find moles of our OH minus first. So if we multiply those together, converting milliliters to liters, I've already done this for you, get 0.001637 moles. Well, since it's all 1 to 1, that's also the number of moles of the acid. Okay, and so now we can convert that to grams, because if we want percent mass, we need to know the grams of acid compared to the total grams of the waste material. Well, this is the total. And so if we can find the grams of the acid, then we can divide those to get the percent mass. Okay, so since everything's 1 to 1, this becomes the moles of the acid. So we have 0.001637 moles of our HC7H5O2. In order to convert to grams, we need the molar mass, so all I did was figure that out by adding up all the atomic masses. So it comes out to 122.118 grams. And if I multiply that, I get 0.1999, so really close to 0.2. And that's grams of our acid. Now, to find the percent mass, I just need to divide. So I'm going to take the grams of my acid, divided by the grams of the total waste material, multiply by 100, and that gives me 56.82%. Let's see, I see 4 significant figures everywhere, so we're going to go with that.